I am here, and I won't say I'm a world expert. I know enough to get how to get myself in trouble. So next slide. So I wanted to start with basically just talking about the risks. So just laying out why do we all care about post-quantum security? And this goes back to the fact that we've known since the time of Shor that effectively one of the things a quantum computer can do is to attack public key infrastructure. And so I kind of wanted to give a view on this. And so I'm going to present some plots here. They're based on 3 papers. The first is this paper on how to factor how to factor RSA 2048 in 8 hours using 20 million qubits. Then there are 2 other papers here that are on elliptic curves. Elliptic curves were always believed to be a more efficient use of resources and to provide better security because they were harder to break classically. And we'll come back to that. But the reality is we all go to HTTPS websites, we do banking transactions, we do everything else. And so public key infrastructure is what protects us. And it is really the handshakes that form the front end of it that cause the problem. It is the authentication, everything else, because that's how we effectively pass the symmetric key or use AES or other things to do the actual encryption, because you don't actually use Shor elliptic curve to do the encryption. It's just the original handshake, authentication, digital signatures that are key. So effectively, when you're done, it is 2 problems. One, you're either doing factorization or it's discrete log version, or you're looking at elliptic curves, which have a discrete logarithmic attack as well. So next slide. So here I am presenting a plot, and let me explain these plots. For elliptic curve key size, which is the bottom x-axis, you just divide the elliptic curve key size by 2, and you get the number of bits of security that's in that elliptic curve. For RSA or Diffie-Hellman, which is kind of the red curve, the yellow and blue curve or elliptic curve attacks from quantum mechanics. But for RSA or Diffie-Hellman, which is the red curve, you have to look at the computational complexity of the general number field C, which is believed to be the most generic general attack. And from that, you can back out and determine the number of bits of security. And so the red curve is really plotted only against the top axis, while all the things are plotted against both the elliptic curve, either the top or bottom, just going from the top to the bottom is just dividing by 2. You look in these algorithms, you ask, well, what is the depth of the code necessary to do this? How many qubits does it take? You can roughly multiply those out. And this gives you some kind of view of what the complexity of solving the problem on the quantum computer is. No error correction, nothing else. It just says, here are the number of error opportunities. And roughly 1 over that number will be the underlying error rate you will have to have in order to successfully complete the computation. Now, I show this in part because it basically shows you that it is easier on a quantum computer to break elliptic curve than it is to break RSA or Diffie-Hellman. So if we go to the next curve, it's just a blow up of this one, next plot. And what I show here is a blow up here, and pre-2015, it's basically the oval on the left that described what the recommended key sizes were for general use. Again, these are the numbers from basically recommended by NIST. Today, we have moved a little farther up the curve to RSA 2048 or elliptic curves of around 224 bits. And these are what we're using today. And so what is crucial here is to understand that on the when quantum comes, elliptic curve, which was thought to be harder to crack classically, is actually easier to break on the quantum computer. So, this is something, a recognition and an awareness. Next slide. So we now understand what the threat is, and so we have to prepare for a world with quantum computers. And the issue is most people believe that a crypto-analytically capable quantum computer, one that has a low enough overall error rate to get through one of these calculations, that this won't happen before the mid-2030s, 2035, maybe 2040, but it takes roughly a decade to replace the public key algorithms. So PKI infrastructure needs to be upgraded. And it needs to be cheap, easily upgradable, patchable, because little problems occur in the algorithm or something else you need to fix, or there's an overflow someplace or something else, you need to put a patch in. And increasingly today, at least one endpoint of almost all connections are wireless. Again, everything I have at home, it's wireless. I do have a wired connection into my wireless box from my FiOS, but that's not optically. So this issue of replacing everything means that I have to do something that's compatible with the technology I'm using at the moment. And of course, what I'm using is wireless. And I don't think QKD solves that problem. So given these attributes, this implies that quantum resistant cryptography is what we're mostly going to use when we're done. The issues with QKD is upgrades typically require new hardware. Hardware remains relatively expensive. Hardware requires fiber or line of sight optical communication. Can't be done on a wire, can't be done wirelessly. So it kind of reads back to what is the role of QKD and quantum communication in quantum internet security? Next slide. And here are some of the possibilities. So quantum communication is essential for connecting or extending quantum devices. And we're going to come back to that as I finish up this slide. QKD also provides a way to inject randomness into the transport layer security, into the TLS. QKD could be useful in back office security or along high value links where people are using inline cryptography in the things. It could be important in a data center or any other high value network as an additional layer of security, because security in depth is something of value. But notice it is mostly some specialized links. I mean, we don't put inline encryptors in most links. And I think the final thing to point out about QKD is why it is the simplest and easiest quantum communication to implement. And so if you can't do it, you can't do any more sophisticated protocols. But I don't think that QKD by itself, other than some specialized links, is going to have a lot of issues. But I want to come back to this point. If you build a quantum computer capable of doing cryptanalysis today, that computer is going to be 50 meters by 20 meters. It's going to be a gigantic machine. And I am going to have coherent communications from one end of the machine to the other. I need quantum networks. I'm not going to build, at least with the technology we currently understand and believe might be viable, I am not going to build a quantum computer capable of doing cryptanalysis without quantum networks. And finally, and just coming back to the closure, there are several papers out there. Everybody would like to find an economically viable problem prior to hitting the place where we start breaking the security of our HTTPS web connections. But today, it appears that the only known problems, known, provable problems, are some things on spin dynamics of small quantum systems and everything else. Almost everything that we know and know how to implement at the moment requires more cycles and more capability. That doesn't mean that we aren't going to find them as the hardware improves, a heuristic algorithm that has economic value. I believe it will happen, but it hasn't happened yet. And so with that, I'm done.